In this video, I want to talk about some review on the different tests, as well as looking at a geometric series and what it converges to. So first of all, looking at these, converge or diverge. This first one, I would, and I'm just going to kind of give you the solution as well as my thinking for each one. I would look at this and I would say, well, if I did a direct comparison to the series 2 over n squared, which converges, okay, that's a convergent p-series. Remember, a p-series is where you have an n to a power on the bottom, you have like a constant on top, n to power on bottom, and the power is greater than 1, makes it converge. So the power being 2 here makes it a convergent p-series. Well, the reason I look at direct comparison is 2 over n squared is a very easy thing to pick out. And if I make the denominator larger, that means that really I made the fraction even smaller. So if this one is so small that it converges, then something less than it must also converge by direct comparison. So this would converge. Okay. Let's go over to the right. This next one could be rewritten as 2 over 7 to the n plus 3 over 7 to the n. Right? I'm going to, right like that. And how I would look at this is I would say this is a convergent geometric series. This is a convergent geometric series. And if I'm adding up two series that converge, then the original series must also converge. Moving over to the right, I would always start by rewriting things with roots and powers as just a power. It will make it much easier to see. The square root of n cubed is the same as n to the 3/2 power. Now again, this is a p-series, right? A p-series is one that has a constant on the top and n to a power. I'm going to put a little box there. A power on the n to a power. If the power is greater than 1, it converges. In this case, it is greater than 1. It is 3/2. So we converge. Okay. Next, I might rewrite this series as 3 times 1 over 9 to the n. It helps very often to rewrite these things because now you say, well, it's a geometric series and the ratio is less than 1. It has to be between -1 and 1 to converge. So this is a convergent geometric series. Another thing that's smart to rewrite are negative exponents. We could rewrite this as 1 over e to the n, which I could rewrite as 1 over e raised to the n. Now, I don't know offhand what 1 over e is equal to, but I know that it's less than 1. So once again, I have a geometric series. Remember, a geometric series is any number, make a little note here, it's any number base being raised to the nth power. And we converge if that number base is between -1 and 1. So this thing does converge. Put a big C over it. And finally, this one, we have, like the one above it, a number over n to a power. But in this case, the power is not greater than 1. So this is a p-series. Remember that p-series notation. That's a constant over n to a power. But this one, because that power is not greater than 1, this will diverge. Use the integral test to determine if the series converges or diverges. Now, usually I don't spend a lot of time even paying attention to necessarily the pieces of a sigma notation, but I want you to see here that this starts at n equals 2. And that's important. Normally, of course, we start at either 0 or 1, but here, if it was the natural log of 0, it would be undefined. If it were the natural log of 1, it would be 0, and we'd be dividing by 0. So that's why, in this case, it has to start at 2. Now, there are a couple pieces with integral tests that we usually don't need to think about a whole lot, but they're worth mentioning. One thing is that to do integral tests, the terms must be positive. And you can see in this case that will be true. I'm going to put a little check, because obviously it's not alternating. There are no negative terms here. Next, it has to be the series, the terms, the sequence must be decreasing. Okay, and that, I hope that's obvious. If the sequence were increasing, obviously the series would not be converging, but it wouldn't even really be checking or worth checking. And here, of course, as the larger and larger values are plugged in, this will continue to get smaller and smaller, so obviously the sequence is decreasing. So integral test says we can create an integral, an improper integral. So for us it would be the integral from 2 to infinity of the sequence, or the series, and evaluate it and see if the integral converges. And if the integral converges, the series converges. If the integral diverges, the series diverges. Now, if the integral converges and we get an answer, that doesn't mean that that's what the series converges to. It doesn't mean that's what the sum is. It just means that that's what it just checks what convergence or divergence. It will never give us an actual number of what it's converging to. I'm going to rewrite this with a limit statement. And do a little work here off to the side. If I think about a substitution where u is natural log, so du is 1 over x dx, you'll see I can take out the 1 over x dx. So this integral, I'm going to just ignore the bounds for a minute. This integral would become 1 over u cubed du, which I could write more easily as u to the negative third du. I raise the power, divide, there's my antiderivative. Okay. So let me kind of continue down here with what I've got. I've got negative 1 over 2u squared, which actually, let me even go further, and let me just write that as negative 1 over 2 natural log of x squared. And let me go back, we're evaluating at b and 2, taking the limit as b approaches infinity. I plug in b, plug in 2, and I'm taking the limit as b approaches infinity. Well, as b gets larger and larger, this denominator will continue to get bigger. 1 over something getting bigger and bigger, the limit is 0. Minus a negative 1 over 2 natural log 2 squared, the answer will just be 1 over 2 natural log of 2 squared. So we can get an answer there. Okay, and because we can get an answer, the integral converges. Okay, the integral converges and therefore the original series converges as well. This last one, sum of a geometric series. Remember, the sum of a geometric series is always the first term over 1 minus the ratio. So this one, you'll notice it's n equals 3. So if I plug 3 in to get the first term, I have 10 multiplied by 5/8 cubed. That's the first term. And then the ratio is 5/8, so 1 minus 5/8. And that's the sum. And if you type that into your calculator, that would give you the sum of the series.